So we should be online soon. Live broadcast has started. So, okay, so it is, I'm Nicola Guicciardini. It is my great pleasure to introduce you to June Barrow-Green, who is one of the foremost historians of mathematics in the late 19th and early 20th century. She holds a doctorate from the Open University, which was supervised by Jeremy Gray. She's now professor of history of mathematics at the Open University and a visiting professor at the London School of Economics. She has written extensively on British mathematics, including the work of British mathematicians during World War I. Following on her PhD, which was published as a book, Poincare and the three-body problem, she has written further about the history of the three-body problem, and she's currently researching the work of Birkhoff and dynamical system theory, the topic of her talk today. She was an editor of the Princeton Companion to Mathematics, working alongside Tim Gowers, and she is a co-author, together with Jeremy Gray and Robin Wilson, of the recently published two-volume textbook on a source-based approach to history of mathematics. She's a winner of the Chandler Davis Prize for Expository Excellence and the 2021 winner of the Royal Society Wilkins-Bernal Medal for her work on the history of mathematics, particularly on the history of women in mathematics and the history of the gender gap. June Barrow-Green is a past president of the British Society for the History of Mathematics and currently chair of the International Commission on the History of Mathematics. Today, as you can see, she will speak about George Birkhoff's forgotten manuscript and this program for dynamics. So, June, the floor is yours.
Thank you very much, Niccolo, for that lovely introduction. Well, my talk is going to be about the work in dynamical systems of the American mathematician George D. Birkhoff, and in particular, as it relates to an unpublished manuscript of his, which is among his papers in the archives at Harvard, and which he wrote almost at the end of his career. Since my publication in the ICM proceedings, I give explicit details about the content of the manuscript. Here, I will focus more on the mathematical background of the manuscript and how it relates to Birkhoff's earlier work, as well as making some remarks about certain parts of the manuscript. So I'm going to begin by telling you something about Birkhoff's career and why he's such an important figure in American mathematics. I'll then discuss his work on Poincare's last geometric theorem. This is a theorem that Birkhoff proved early in his career, and it also features in the unpublished manuscript and in many other publications in between. So in a sense, you can think of it as bookending his work in dynamics, as well as providing a common thread. I will then say something about his work in dynamical systems in general, particularly focusing on his book of 1927, before moving on to discuss the unpublished manuscript, its origins, contents, and the reasons why it remained unpublished. Well, on this slide is a brief overview of Birkhoff's career, and I've highlighted at the bottom some significant events. Birkhoff was born in Michigan. He studied first at the Lewis Institute of Technology in Chicago, then moved to the University of Chicago, where he came under the influence of Maxime Bochet, before then, completing his undergraduate degree at Harvard. He returned to Chicago for his PhD, and I'll say a little more about this in a moment. His first position was at the University of Wisconsin, and he then went to Princeton, where he began what would become a lifelong friendship with Oswald Veblen. And it was while he was at Princeton, he published a paper on the general theory of linear difference equations, which first brought him to prominence in the American mathematical community. Then in 1912, he took up a position at Harvard, where he remained for the rest of his life, and I'll elaborate more on this. Birkhoff First, I want to say something about the University of Chicago. When Birkhoff returned to Chicago in 1905, it was to study for a PhD under E.H. Moore. Moore was the first head of the mathematics department in Chicago, the university being founded in 1891. And Moore had studied in both Göttingen and Berlin. And he'd built a strong department in Chicago, including mathematicians from Germany, Oskar Bolzer and Heinrich Maschke. And during the early years of the 20th century, the University of Chicago was considered the leading institution for higher mathematics in America. Moore himself became well known for his general analysis and for his work in mathematics education. And he would have a great influence on Birkhoff. And in 1938, Birkhoff described this to Raymond Archibald of Brown University, who at the time was preparing the semi-centennial history of the American Mathematical Society. Birkhoff acknowledged his debt to Moore, whom he described as having the true fire of genius within him. And as he wrote to Archibald, "My work for my degree at Chicago was all formally done under the direction of Moore. Although as a matter of fact, I obtained all the material necessary from my courses at Harvard and from outside reading, and suggested my own subject, which was in a field outside of Moore's province. However, I feel especially grateful to Moore for impressing me with the importance of the abstract domain and for stimulating me on the abstract side." And two important points to note here. Firstly, Birkhoff's reference to outside reading. Even as an undergraduate, Birkhoff was immersing himself in the works of Poincare, particularly Poincare's great treatise on celestial mechanics. As Marston Morse would later write, Poincare was Birkhoff's true teacher. And secondly, about Birkhoff's comment about Moore stimulating him on the abstract side, since, as will become evident, this characterizes his approach to the theory of dynamical systems, where he was motivated by the abstract rather than by concrete problems. Now to Harvard. Birkhoff joined Harvard as an assistant professor in 1912, being made a full professor in 1919. He was one of the leading American mathematicians in the interwar years, and he held several distinguished offices, including president of the American Mathematical Society and president of the American Association for the Advancement of Science. He gave 2 ICM plenary lectures, and he was president-elect of the ICM that was due to take place in Cambridge in the United States in 1940, but which was postponed due to the war and did not take place until 1950, which was after Birkhoff's death. As well as the theory of dynamical systems, Birkhoff also did important research in differential equations, in difference equations, as well as making contributions to the 4-color theorem and relativity. And towards the end of his life, he became interested in mathematics and aesthetics and developed a theory of aesthetic measure. Altogether, he published some 120 papers and 5 books. Now, of particular importance was his role in nurturing doctoral students. He supervised 45 PhD students, including 3 from the Radcliffe College, the College for Women. And on the slide, you'll see the names of some of his better known students, such as Marston Morse, Marshall Stone, and Hassler Whitney. But Birkhoff did not only supervise his students, he helped them, and indeed other students, to establish their careers in many universities around the United States. So I'm now going to turn to Poincare's last geometric theorem. This was one of the enduring elements of Birkhoff's work. In 1912, Poincare did something unprecedented in his career. He published a theorem he'd been unable to prove in generality, but it was a theorem that was of great importance to him, and it related to his earlier seminal work on celestial mechanics, and in particular, his Oscar Prize-winning memoir of 1889 on the 3-body problem, and on his great treatise, the one in which the young Birkhoff had immersed himself as an undergraduate. It was a theorem he'd been working on for 2 years previously, and he introduced the paper in the following way. Some time ago, I proved the existence of periodic solutions in the 3-body problem, but the result left something to be desired, because if the existence of each type of solution was established for small values of the masses, it was unclear what would happen for larger values, what solutions remained, and in what order they disappeared. Reflecting on this question, I became sure that the answers depended on the truth or falsity of a certain geometrical theorem, the statement of which is very simple, at least in the case of the restricted 3-body problem, and in dynamical problems with only 2 degrees of freedom. So what is this theorem? This is essentially how Poincare stated it. You're given a ring formed by concentric circles of radii a and b with a greater than b in the xy plane, with xy being polar coordinates, and you have a one-to-one continuous area-preserving transformation of the ring into itself. And this advances points on the outer circle in the clockwise direction and on the inner circle in the opposite direction, and by varying amounts in each case. Then the theorem says there will exist at least 2 points of the ring invariant under the transformation. Now, the significance of the theorem is that if it's true, it proves the existence of infinitely many periodic solutions in the restricted three-body problem. So the restricted three-body problem, I should tell you, is a particular case of the three-body problem. And it's one where you have two large bodies moving in circular orbits around their common center of mass. And the third body, which is minute with respect to the other two bodies, you could consider it to be equivalent to a speck of dust, for example. This third body moves in the same plane as the other two bodies. And the problem then is to ascertain the motion of this third body. Now, it may sound very artificial, but in fact, it's not a bad approximation to the Sun, Earth, Moon system, where the problem is to ascertain the motion of the moon. Now, despite working on this theorem for so long, Poincare had been unable to prove it except for a few special cases. But an important issue here is the publication history of the problem. It was on the 9th of November 1911 that Poincare wrote to Giovanni Guccia, the editor of the Rendiconti di Cercolo di Palermo, to ask him if he'd publish an incomplete memoir. Well, of course, Guccia said yes. Any journal editor at that time being offered a paper by Poincare, however incomplete, would have leapt at the chance to publish it. The paper, which was dated the 7th of March 1912, was published 2 months later at the beginning of May. But only 10 weeks later, on the 17th of July, Poincare died unexpectedly in Paris. It was almost as if he knew he would not live long enough to prove the theorem. But then on the 26th of October that year, Birkhoff presented his proof to the American Mathematical Society, and the following January, it was published in the Transactions of the Society. Given how long Poincare had been working on the proof, Birkhoff's speed was remarkable. Master Morse reported that Birkhoff had been urged on by his colleagues to find the proof, while Marshall Stone reported the rather remarkable claim that Birkhoff was working so hard that he lost some 30 pounds in weight in the course of finding the proof. But Birkhoff was not the only mathematician to rise to the challenge. After all, what mathematician would not want to prove a theorem that had baffled Poincare? But no one was better prepared than Birkhoff. In the paper, Birkhoff himself admitted that for some years he'd been considering questions of a character similar to that presented by the theorem, and that the methods he'd been using turned out to be applicable. Now, one of those who tried to prove the theorem was Elie J. Brouwer. There is a correspondence between him and Diederik Korteweg about it, as well as a long, almost undecipherable manuscript containing an unsuccessful attempt at a proof. But when Brouwer saw Birkhoff's proof, he wrote to congratulate him. The Swedish mathematician Edvard Fragman was another who tried to prove it. It was not surprising that he should be attracted to it, as he was the mathematician who back in 1889 had the task of editing for Acta Mathematica, Poincare's Oscar Prize-winning manuscript on the three-body problem. Now, unsurprisingly, Birkhoff's proof attracted a lot of attention, particularly in the United States and in France. But it's quite interesting to see that in Germany, the reaction appears to have been rather more muted. Birkhoff's friend and colleague, Veblen, was traveling in Germany at the end of 1913, and he wrote to Birkhoff from Berlin. After 10 weeks in Göttingen and 4 weeks in Berlin, I'm beginning to have a definite impressions of Germany. Mathematically, even more than politically, it is a monarchy. The mathematical situation is well illustrated by a remark of Landau's when I asked him whether there was any interest in abelian functions and the like. No one in Germany is interested in anything Hilbert has not worked with. They're only mildly interested in what is going on elsewhere, unless it touches pretty directly on their own work. Gronvoll has made an impression on Landau and his circle, and your proof of Poincare's theorem has created the impression that you probably have to be reckoned with. I was amused, however, to see how little the people in related fields really know about your work. I was present when Kari Theodori opened a batch of reprints from you. His comment was, he seems to cover a great many subjects. Well, needless to say, in the many obituaries of Birkhoff, the proof figures prominently, but perhaps nowhere more prominently than the obituary by Jacques Hadamard for the Académie des Sciences, where he devoted more than 1/3 of the obituary to the theorem. And in the whole obituary, he managed to mention Poincare's name more often than Birkhoff's. Particularly interesting are the remarks by Norbert Wiener, especially since his relationship with Birkhoff was not always harmonious. In his autobiography of 1953, Wiener remembered the moment of Birkhoff's proof well. At that time, a star of the first magnitude had appeared in the firmament of the Harvard Mathematics Department. It was G.D. Birkhoff. In 1912, Birkhoff, then 28, had astonished the mathematical world by solving an important problem in dynamical topology, which had been put but never solved by Poincare. What was even more remarkable was that Birkhoff had done his work in the United States without the benefit of any foreign training whatever. Before 1912, it had been considered indispensable for any young American mathematician of promise to complete his training abroad. Birkhoff marks the beginning of the autonomous maturity of American mathematics. And indeed, Wiener made an important point here. Birkhoff was part of the first generation of American mathematicians not to go to Europe to complete their mathematical training. In fact, perhaps even more remarkably, despite his success with Poincare's last geometric theorem, Birkhoff didn't make his first trip to Europe until the early 1920s. Now, as you can see from this list, Birkhoff retained an interest in Poincare's last geometric theorem throughout his life. His original paper was quickly translated into French, the translation being arranged by Hadamard, and Birkhoff himself later corrected a minor omission from the original paper. And discussions on the theorem, or extensions of it, appear in several of his publications, as for example in his book of 1927 on dynamical systems, where he devoted a whole chapter to extensions of the theorem. So I'm now going to move on and talk about Birkhoff's work in dynamical systems in general. And here I've listed the most important of Birkhoff's papers concerning the theory of dynamical systems. Reading these papers, the influence of Poincare is profound. As the Russian mathematician Nikolai Krylov said in 1924, Birkhoff is the Poincare of America. And like Poincare, Birkhoff made the periodic motions central to the theory. Particular highlights include his paper of 1915 on the restricted three-body problem, which won the Carini-Stampaglia Prize of the Royal Venice Institute of Science. In this paper, he made the first qualitative attack on the restricted problem since Poincare. But unlike Poincare, Birkhoff made little concession to analysis, and his investigation was founded almost entirely on topological ideas. Another highlight is his paper of 1917, which was awarded the Bochet Prize of the American Mathematical Society, and which later Birkhoff said he thought was the best piece of research that he was ever likely to do. In this paper, he developed various methods for establishing the existence of periodic motions, including his minimum method and his minimax method, and the latter later providing a starting point for the work of Marston Morse on the calculus of variations in the large. It was also in this paper that Birkhoff first began to generalize Poincare's idea of a surface of section and formally develop a theory attached to it. Poincare had used the idea specifically to reduce the restricted three-body problem to the transformation of a ring into itself. But if the method was to have a general validity, it was important to establish under what circumstances surfaces of section exist. Birkhoff was able to show that not only do they exist in a wide variety of cases, but they can be of varying genus and have different numbers of boundaries. A feature of Birkhoff's paper of 1927 on the periodic motions of dynamical systems, which had been written on the invitation of Mittag Leffler to celebrate the 50th anniversary of the journal Acta Mathematica, was his introduction of the billiard ball problem, which he used to show how Poincare's last geometric theorem could be applied to dynamical systems with 2 degrees of freedom. It's indicative of this paper's status that in 1987, it was selected by Robert Mackay and James Mice for reproduction in their book on the most significant writings on Hamiltonian dynamics published since the First World War. Now, as well as his papers, there is, of course, Birkhoff's influential book on dynamical systems, which derived from his AMS colloquium lectures of 1920, although the book itself was not published until 1927, and there was a second new edition, which appeared in 1966. Now, though representing essentially a continuation of Poincare's work on celestial mechanics, the book opened a new era in the study of dynamics by detaching it from its origins in celestial mechanics and making use of topology. It provides a summary of Birkhoff's research in dynamics during the preceding 15 years, with the final 3 chapters on the general theory of dynamical systems, the case of 2 degrees of freedom, and the three-body problem, bringing together the main strands of his work. Excuse me. As Bernard Koopman, one of Birkhoff's former students, remarked, dynamical systems is better described as a theory than as a book. Birkhoff's goal was clear. The final aim of the theory of the motions of a dynamical system must be directed towards the qualitative determination of all possible types of motions and of the interrelations of these motions. The book was well received when it first appeared, but that said, this was a period when the subject was in some sense at a crossroads. Its main domain of application, celestial mechanics, no longer had the status it possessed in the 19th century. The end of the 19th century had been crowned by Poincare's 3-volume treatise, the final volume appearing in 1899. But in the early decades of the 20th century, other subjects had begun to dominate. This was the time of relativity theory and quantum theory, two subjects which would revolutionize physics. Furthermore, by insisting on general problems of dynamics rather than particular ones, and by looking globally at sets of motions rather than particular ones, Birkhoff's approach was extremely original. It is not therefore surprising that the book fell almost into oblivion for a while. That is until the modern development of chaos theory, when it once again came into its own. So in a sense, we can see dynamical systems as a fundamental link between the work of Poincare and modern work. The 1920s was also a period in which Russian mathematicians began to show great interest in Birkhoff's work. For example, in October 1926, Pavel Alexandrov wrote to Birkhoff to ask him for copies of his papers, including the ones on Poincare's last geometric theorem. As he said, "All of your work is of the greatest interest to us in Moscow, especially since we have a group in my topological seminar which deals particularly with your research. In our topological seminar, we're going to study your work even more closely." And at the beginning of 1936, Birkhoff was invited by Andrei Markov to speak at a functional analysis conference in Leningrad. The mathematicians there wanted to hear him talk about his ergodic theorem, the famous theorem he'd proved in 1931. But Birkhoff never made the trip. A few months later, he was informed by Markov that the conference had been cancelled. This was, of course, for political reasons. But at the same time, Markov also reported that the Russian translation of the text of dynamical systems, including Birkhoff's papers on Poincare's last geometric theorem, had been completed. In fact, the Russian translation of dynamical systems did not appear until 1941, and it was reprinted again in 1999. It also included a number of Birkhoff's papers, including those on the ergodic theorem, as well as those on Poincare's last geometric theorem. However, the translators did find some errors, and they didn't flinch from pointing them out. Although conceding that the theorems were correct, it was just that some of the proofs needed attention. And indeed, in the 1966 English edition of Dynamical Systems, a number of errors were also corrected. Now, alongside his papers on dynamics, Birkhoff also began to present a program for research in dynamics. In 1928, he gave a series of lectures in Berlin on some problems in dynamics, and the lectures were published in German in a condensed form. In these lectures, having emphasized the importance of qualitative dynamical ideas for the exact sciences, he discussed various examples, including the billiard ball problem, the motion of a particle on a smooth convex surface and on a smooth closed surface of negative curvature, and he also discussed the three-body problem. 9 years after his lectures in Berlin, Birkhoff returned to the same theme, but this time in Paris. In 1937, he gave a lecture at the Poincare Institute on some problems of dynamical theory. Birkhoff referred to this lecture in a footnote of the unpublished manuscript, where he said that in Paris he had made reference to, and I quote, "one or two of the problems listed in the present paper," end of quote, but without identifying which ones, and no further information on this lecture has so far come to light. So this brings me to the unpublished manuscript. And as we shall see, this derived from a lecture he gave at the University of Chicago in 1941, of which a summary was published in Science at the end of that year. Now, in my discussion of the manuscript, I'm going to begin by looking at its genesis and why it was left unpublished before examining some of its contents. In September 1941, the University of Chicago celebrated its 50th Jubilee. It was a celebration that had been 2 years in the planning, honorary degrees were awarded, and a symposium was held in conjunction with the American Association for the Advancement of Science. According to an account in the university magazine, the celebration was, and I quote, sufficiently significant that in a world at war, it attracted national and even worldwide attention. However, this does seem to have been a little of an exaggeration. Nevertheless, it was certainly an elaborate affair. Now, as one of the leading figures in American mathematics and a former student of the university, Birkhoff was a natural choice for an honorary degree and symposium speaker. The citation describing him as the leading contributor to the fundamentals of dynamics. The other mathematician amongst the 34 others on the rostrum was Birkhoff's close friend and long-standing colleague, Oswald Veblen, also a Chicago protege. For the subject of his lecture, Birkhoff chose some unsolved problems of theoretical dynamics, a topic well in keeping with the 50th anniversary theme of the university, New Frontiers in Education and Research. The lecture was ready only about a week before it was due to be delivered, as Birkhoff admitted to Eric O'Connor, one of his former doctoral students. During the last few weeks, I've been extremely occupied with the address, which I have to give next week in Chicago. In it, I take a look at classical dynamics from the abstract point of view and suggest about a dozen problems, many of them new, which seem to be most directly in the line of further advance. In one or two instances, I indicate a partial answer to these. It now looks as though the paper will be in good shape for the 24th of September when I have to deliver it, but it will be a very close squeak. Well, as well as the unpublished manuscript in the Harvard archives, there is in the University of Chicago archives a copy of Birkhoff's press release, which was written before he gave the lecture. And this began, as was first realized about 50 years ago by the great French mathematician Henri Poincare, the study of dynamical systems, such as the solar system, leads directly to extraordinarily diverse and important mathematical problems in potential theory, topology, and the theory of functions of real variables. He concluded, one of the last of these problems will perhaps excite the most interest, since it embodies a conjecture which in a certain sense yields a kind of supplement to the famous last geometric theorem of Poincare. Now, in this press release, he referred to only 10 problems, but without describing them. Although, as we shall see, in the end, the number of problems increased to 17. Now, Birkhoff received the Chicago invitation in November 1940, and in April 1941, he was invited by Otto Schmidt and Anisim Bermant to contribute to the Jubilee volume of Mathematische Schabonik, due to be published in 1942 to celebrate 75 years of the journal's existence. Birkhoff cannot have taken long to decide that an article laying out his program for dynamics would make a fitting contribution to the journal, knowing that the Chicago meeting would provide him with an excellent opportunity to test out his ideas before committing them to print. In May 1943, Birkhoff wrote to his Russian colleagues to say that he had not wholly completed the article, mentioning that he had spoken on it in a preliminary way in Chicago, but that he had decided to delay sending it to Russia until hostilities had ceased. But of course, that was not to be. In 1944, Birkhoff, aged only 60, died unexpectedly. Thus, the manuscript was never submitted to the journal and remains among Birkhoff's papers in the Harvard archives. Some 3 months after the lecture, a 3-page summary of it appeared in the journal Science. In fact, before Birkhoff delivered his lecture, he'd been asked by the journal Nature if he could provide them with a summary. But for whatever reason, it's not known, Birkhoff chose to publish the summary in Science. It's certainly the case that the editor of Science was keen to get papers on mathematical subjects, although he was concerned about accessibility, since, as he told Birkhoff, the English used by mathematicians is not always understood by other scientific men. In the summary, as well as giving brief descriptions of the problem, Birkhoff gave a pathway for the development of his ideas. He traced them from Poincare, who first realized that the study of dynamical systems led directly to problems in topology, on through the abstract ideas of E.H. Moore, describing how these ideas fed into his own work. Now, although Moore deserved a high billing, it was also a diplomatic move on Birkhoff's part to be explicit about the contribution of Moore, his thesis advisor and first head of the university's mathematics department. In the manuscript, the reference to Moore, although laudatory, is abbreviated and consigned to a footnote. And I'm now going to move on to the manuscript itself. So on this slide, I've listed the contents of the manuscript. Altogether, there are 14 sections, beginning with an introduction and ending with an epilogue. It begins with, after the introduction, we move on to a couple of sections of general theoretical background with terms being defined and so on, and then becomes the listing and discussion of the problems. And altogether, there are 17 problems. The first 10 are formulated in terms of abstract spaces. The 11th is concerned with extensions of results of Carl Sundman on the three-body problem, and it's extending Sundman's results to the motion of a gas. And the last 6, which are concerned with n-dimensional spaces, are of a topological nature. And the paper is also divided up into sections, which imposes a useful classification on the problems. And it also includes, the manuscript also includes a provocative form of conclusion. Now, since in the press release, as I've mentioned, Birkhoff referred to only 10 problems without listing them, it's possible that he had originally intended to present only 10 problems, and it was in expanding the paper that led to the close squeak that was mentioned above in the letter that I quoted, where he said he was very close to the deadline before finishing it. So to set the scene and to give a clear idea of Birkhoff's intentions, it's worth quoting the opening words of the manuscript. It scarcely seems too much to say that all the basic problems of point set theory, topology, and the theory of functions of real variables present themselves naturally in purely dynamical contexts. Some of these dynamical problems are best formulated and solved in terms of an underlying abstract space, as important recent Russian and American work has shown. Others are inherently of more special character. In the present paper, I venture to set forth certain unsolved problems of this type, which seem to me worthy of further study. The problems are arranged as much as possible in order of decreasing abstractness. They're formulated in terms of positive conjectures, in the belief that this procedure is most likely to stimulate further research. In each case, indications of the underlying reasons for these conjectures are made, some new definitions are given, and some partial results are deduced, and so on. Now, I shall now describe a few of the problems, beginning with the first. The first problem, which is a conjecture about the interrelationship between continuous and discrete flows in an abstract space, is precursored by 3 sections on continuous and discrete flows, including an explanation of geodesic flow. As Birkhoff observed in a footnote, the idea of using this kind of abstract setting for a dynamical problem did not originate with him, but in an article of 1933 by Hassler Whitney, one of his doctoral students. Now, the idea is that in that abstract space, which is a compact metric space, a type of reduction of a continuous flow to a discrete one may be effected by showing that there exists a surface of section in the abstract space on which the flow can be studied. So each point in the space represents a state of motion, and as time passes, there's a steady flow of the space into itself, with each point tracing out a curve of motion, each curve representing a complete motion of the dynamical system. As Birkhoff noted, he had already shown, and I quote, "In the n-dimensional case, and very recently, Ambrose and Kakutani had established in the abstract case a kind of converse reduction of a continuous flow to a discrete flow may be made, providing one is content to introduce discontinuous flows." Now, Birkhoff's hope was for a more complete result, and he felt that the conjecture would be shown to hold. Since he did not give a citation for the Ambrose and Kakutani paper, which had been submitted for publication in 1941 and which was published in 1942, it would appear that he did not return to the manuscript in the years following the lecture. So I'm now going to jump to problem 11, where Birkhoff asked for the generalization to a gas of certain remarkable results on the 3-body problem, produced in the early years of the 20th century by the Finnish mathematical astronomer Carl Sundman. Birkhoff was a strong advocate for Sundman's theoretical solution to the 3-body problem, which, due to its practical limitations, had met with a mixed reception. He'd even gone as far to say that the recent work of Sundman is one of the most remarkable contributions to the problem of 3 bodies which has ever been made. Now, of particular relevance here are Sundman's results concerning triple and binary collisions, namely that a triple collision can occur only if all 3 integrals of angular momentum are simultaneously 0, and that the singularity at binary collision is of removable type. Now, Birkhoff had already shown in his book of 1927 how the essence of Sundman's article can be used under other laws of force and for a system of more than 3 bodies to establish that, with similar initial conditions, a simultaneous near approach of the bodies cannot occur. Hence, the generalization to a gas was a natural next step. The problem was formulated rather vaguely. Indeed, in the summary, he admitted it was incomplete, but he chose to include it because it provided, and I quote, "an interesting illustration of a dynamical flow in a kind of Euclidean space of infinitely many dimensions, intermediate in type between the flows in abstract metric space and in n-dimensional Euclidean space." Following on immediately from problem 11, Birkhoff now turned to problems relating to motions in n-dimensional space. Problem 12 is essentially the first problem he presented in his Berlin lectures in 1928, and which would be solved by Meyer in 1946. But he now extended it to the n-dimensional case. On this occasion, Birkhoff used the notion of wandering motions of a space, a notion he'd introduced in his book Dynamical Systems, and which he described, none too clearly, I think it must be said, as, and I quote, those which can be embedded in a molecule which never overlaps itself as time increases or decreases. Now, when the wandering motions are removed from the space, there remains a closed subspace of lower dimension, which can then be considered from the same point of view. Using this idea, Birkhoff formed a well-ordered set of subspaces, which is innumerable and terminates in the set of central motions. Emphasizing the fact that in the known cases, the series contain at most n terms, the problem he proposed was to construct a continuous flow in a closed manifold of greater than 2 dimensions, for which the well-ordered set of subspaces leading to the central motions contains more than n, and if possible, an infinite number of terms. Now, in the final 2 problems, Birkhoff returned again to Poincare's last geometric theorem. Unsurprisingly, he thought these 2 problems, since they express conjectures, which in a sense represent a complement to the theorem, were the ones most likely to generate interest. In problem 16, Birkhoff conjectured that periodic points would exist in the case when the points on the 2 concentric circles are advanced by the same angular distance. That is, their rotation numbers alpha are equal, provided, in this case, that some nearby points of the ring become separated widely in an angular sense when the transformation is repeated sufficiently often. And this is the same as what happens when the rotation numbers are unequal, which is the case of the original theorem. He followed this by a conjecture on the partial converse, the case when the common rotation number alpha is not a rational multiple of 2 pi. In the 17th and final problem, Birkhoff considered the same hypotheses as in problem 16, but with an additional condition concerning the angular separation of pairs of points on the ring. And he conjectured that this again would imply the existence of periodic points on the ring. And in the last part of the paper, Birkhoff applied the result to the planar restricted 3-body problem, describing the actual case of the Sun-Earth-Moon system as described earlier. And it was this application that led him to what he described as a provocative form of conclusion. And this was a potential result concerning the behavior of certain lunar orbits. Birkhoff ended the manuscript with the following. In concluding this unusual form of paper, I venture to hope that the conjectures made will accelerate further advances. However, it must be confessed that most of these problems present difficulties which may be difficult to surmount. Well, with regard to the second remark, history, at least so far, would seem to indicate that he was right. So now I want to look at responses to the lecture, but in fact, responses to the lecture and to his publication in Science have been difficult to find. But this is perhaps not so surprising given the timing, because the United States entered World War II in December 1941. So I think it's reasonable to conjecture that American and European mathematicians would have had other things on their mind. And after the war, these ideas of Birkhoff's don't seem to have been picked up. The fact that Birkhoff's summary was published in Science rather than a mathematics journal would also have meant that its chances of being seen serendipitously by mathematicians would have been reduced. And of course, by the time the war was over, Birkhoff had died. Now, we do know from the Polish-American mathematician Stanislaw Ulam, who had first met Birkhoff a few years before, shortly after he'd arrived for a visit to Princeton. We know from Ulam that there was talk about Birkhoff's lecture because he'd heard reports of Birkhoff's extremely interesting talk, and he asked Birkhoff for a copy of the summary. There was certainly concrete interest shown by the Japanese-American mathematician Shizu Kakutani, now known for his eponymous fixed point theorem proved in 1941, and one of the co-authors of the paper I mentioned earlier, since he told Birkhoff in January 1942 that he was hoping to solve one of the problems, but he did not say which one, and he didn't, as far as I can ascertain, publish on any of them. Now, Kakutani had come from Japan to Princeton in 1940 on the invitation of Hermann Weyl, and he'd met Birkhoff on several occasions. But when the US and Japan went to war at the end of 1941, he returned to Japan. So, of course, any opportunities for personal discussions with Birkhoff were then curtailed. As well as there being little overt response to Birkhoff's lecture and publication in Science, Birkhoff is not an easy read. As Walter Gottschall, one of the founders of topological dynamics, an author, together with Gustav Hedlund, of the founding text on the subject, wrote in the year 2000. Somewhere, I read that G.D. Birkhoff once said that if he thought mathematics exposition to be important, then he would be the world's best expositor. Birkhoff was certainly not the world's best expositor, and indeed he came close to the extremum in the other direction. In dynamical systems, the style of writing he adopted was so inadequate in clarity and precision that almost any beginning reader had to be discouraged from continuing. While I consider this to be rather harsh, and especially since Gottschall himself did not have a reputation as a good expositor, there is certainly an element of truth in it. Gottschall's opinion did, after all, chime with the Russian view. Even Jürgen Moser, in his introduction to the 1966 English edition of Dynamical Systems, conceded that to the modern reader, the style of the book may appear less formal and rigorous than is now customary, but nevertheless acknowledging its inspirational role. In addition, I've shown the manuscript to a number of mathematicians in the field, and without exception, they found it hard going and have been very puzzled by it. Thus, there remains further work to be done. Work to determine the extent to which Birkhoff's problems have been tackled, if at all, and to what effect, in order to ascertain whether, in the final analysis, Birkhoff was on the right track after all. Thank you very much.
So thank you so much, June, for this wonderful talk, and thanks to the audience for attending. I wonder whether are there any questions? I don't see any. We have just a few minutes. Maybe I might ask you, June, I've seen that several students, PhD students, were women. Does this fit with your research on women in mathematics at all?
Actually, I haven't looked at his students. It's a bit late for the work I'm doing at the moment on women mathematicians. Concentrates a bit more on the late 19th, very beginning of the 20th century, but that's a good question. I know there has been quite a lot of work done in the States by historians of maths on PhDs, women PhDs, and it's kind of not a sort of linear progression. One might expect that women PhDs would gradually, hopefully you get more and more of them, but they go up and then they come down and then they go up again, and there's kind of quite a complex story. And for anyone interested in that particular question, the IMU website, the Women in Maths website, has got lots of sort of information and resources about sort of history of women in mathematics, and particularly I think there's quite a lot about women, American women mathematicians of the 20th century.
So I don't see, I see that we have only 1 minute left, so I think it is a good idea if we thank again June for this her wonderful talk and for attending, and I think we can end here.
All right, thank you very much.